Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Jirong Mao with us today. Hello, Jirong.
Hello, Editor Frank. Hello, everyone.
Awesome. And Jirong, where are you located at? What's your geolocation?
Um, Actually, now I'm in my office, the Yunnan Observatories. That is the city. The city name is Kunming, and that is a nickname of the city, like
Okay.
Spring City. It
Huh?
means the weather is very good. So always the spring you get. So it's in the southwest of China.
Huh?
So that's
Very
just a
cool.
beautiful city, and there is an observatory. So
Very
I'm
cool.
working there.
Sounds like a beautiful place. I'll have to visit someday.
Yeah, yeah, that's right.
Good. And it is September 15th of 2025 as we record this. And is it still spring-like where you're at or moving into fall or always spring?
Yeah.
It's always spring. Okay, good. Let's see. And I'm in Phoenix, and we are coming out of our very hot summers, and we're starting to cool off a little bit, and we're getting into somewhat of our fall weather. So it'll be very nice soon. So that's good. And Jirong, what do you like to do for research?
But basically, working on high energy astronomy, and so usually I work on so-called multi-wavelength observation, X-ray, basically X-ray and optical for high energy transients. And in my PhD year, I worked on galaxy formation and evolution, basically a hydra shift. But now my focus on high energy transient. But in the meanwhile, I also working on some theoretical models. Basically, this is a paper we want to show. This is about a numerical simulation. So this is the things I'm working on.
Very cool. So you're sort of a double threat. You do both observations and theory.
Hopefully can do both.
Very good. Very good. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Low
Uh,
angular, low angular momentum, black hole accretion. First general relativistic magnetohydrodynamic evidence of standing shocks. And Jirong, take us away.
Okay, this is a paper about the black hole accretion. This is we use so-called GRMHD to search the evidence of standing shocks. So first, please allow me to introduce the collaborators. I really appreciate my collaborators. For example, Yusuke Mizuno, because we use the GRMHT code, which is called Black Hole Accretion Code, BHAC,
Yes.
and Yusuke Mizuno works on this kind of code. So I really appreciate him and his collaborators for this kind of code. I also appreciate, for example, Shigehiro Nagataki, and we communicate since long ago for the numerical simulation technical problems and scientific aims about this. And I also appreciate Indu Dihingya, and he already proved some hints about the standing shock from roughly speaking simulation, and I think that is very great if we can find some evidence of standing shock. So I really appreciate our collaborators about this excellent paper and results.
I agree. It's an excellent paper and results. Good shout out. Good shout out. Okay, let's go. Introduction. Here we go.
Uh, yeah, before introduction,
Okay.
like to just introduce a little bit about the way of simulation. That is my very private opinion about the numerical simulation. We know that astronomy is an observational science. So we use space telescope, ground telescopes to do observation. So that is definitely correct. But
Yes.
in the meanwhile, we do theory. So we use computers. So this is kind of numerical simulation. But in my opinion, of course, some people has also roughly speaking same opinion. That is not only theoretical modeling, theoretical simulation, but a theoretical experiment. We use same situation like we have computer clusters, and we can do uh, some kind of so-called observation to use computer clusters in the labs. This is also kind of experiment, so we may say numerical experiment in the labs. So this is, I think observation is by telescope is important, but also simulation in the labs is also important.
Yes.
This is the technical point. Let's say we may focus on. This is my biased opinion, but I would like to say
Oh, I
that.
agree. I agree. I agree.
Uh, yeah. Okay. So for introduction, this is uh, we can say straightforward to say that or we have a discussion about standing shock in accretion flow. That is a long-term discussion about that. So
Hmm.
different groups have different opinions and different ideas, and they have great efforts on this topic. But
Yes.
we should search to get the evidence of the standing shock. So this is quite a simple aim to get the result to have this paper. Of course, we have very complicated accretion physical process, and we have complicated analytical, semi-analytical models, but this is just the background. And the final aim is we want to search the feature of the accretion. This is our final aim. It is straightforward, but we can say that that kind of accretion uh, is a is a bit special. It's not like we usually get the traditional angular momentum transfer accretion flows, but we focus on the low angular momentum flows.
Yes.
That is one key point we can play in our accretion simulation. So we get this low angular momentum flows and to check if the standard shock is in the low angular momentum accretion mode.
I'm
This
with
is
you.
also one background of this paper.
I'm with you. Yes, I'm with you. Hmm. Okay.
And then we can see that we have a low angular momentum flow that we considered in the magnetohydrodynamics. So this is MHD
Yes.
flow. Of course, some people already checked some cases in the hydro simulation, and but we think maybe we can develop it with the case if we consider a magnetic field. So things could be similar or things could be changed. So we take into account the effect of magnetic field. This is
Good.
another point we can consider. And it's not only this. We have hydro simulation or MHD simulation, but we should consider the GR MHD, since general relativity is important if we consider the accretion modes, accretion physical process near black hole horizon. So if so, we should consider the different black hole, for example, black hole spin cases to the accretion effect. So basically, we need a simulation in the framework of general relativity. This
Cool.
is the another background we take for the GRMHD. And if we have GRMHD, and if we get some hydrodynamic features like standing shock, but basically we cannot use a telescope to observe the dynamical process like standing shock. However, we can link some dynamical process to some observational features.
Cool.
For example, so-called QPO signals. These QPO signals, we treat signals have different physical explanations. We don't know yet the physical origin of QPO, but maybe our simulation can provide one interesting explanation to zoom in the QPO physical process. This is one observational aim for our astronomy field to provide our physical interpretation. This is also one background for us.
Good. I'm with you.
And so basically, if we talk about simulation, we have 1D simulation, 2D simulation, or 3D simulation. So here we first try the two-dimensional simulation, and then we get the parameters that we want to explore, and we use the results from 2D extended to 3D, and we get again 3D simulation results. That is also people usually play like this.
Yeah.
And okay, and just additional situation is in black hole accretion research field, we can just divide it like if magnetic field is strong, we say, okay, we have the mad accretion flow. Opposite, we can have so-called the SANE same regime. We just to take into account this difference, and we can go on just to distinguish the accretion the standing shock is in the mad case, or the standing shock is in the sine case.
Good.
This is just to fit the accretion flow modes.
Cool. I'm with you. Okay.
Okay, so this is just the method. Okay, this is just the code we can focus on. So again, we say we use the black hole accretion code, which is nowadays one of important GRMHD code people use.
Yes.
So we use this black hole accretion code to do our simulation.
Good. Always good to give software a shout out. Okay.
Okay, so the second part is the method we use and the simulation we want to set up. So the simulation domain we just extended to 2500 RG, and we set up the effective resolution, and we just define the RG and the TG, and the numerical simulation is carried up to 15,000 TG, and So this is, I mean, generally we describe the simulation setup.
Good.
The important thing is we do like some other researchers do exactly the same. We use a very important thing is we use Fishbone and Moncrief torus. This is FM torus.
Yes.
We just use this kind of torus and we play all things on the torus to play the accretion. So this is one important thing. And of course, some people like saying that they go to the global solution and they start far away from the black hole center and they
Yes.
go on to the accretion. But this, roughly speaking, are same. So for simplicity, we use this FM torus to play all things.
I'm with you.
And
Yep.
yeah, okay. If we use the FM torus to do the situation, we can directly play just now we said the low angular momentum. So we arbitrarily try to introduce a low angular momentum parameter. For example, here we just we first tried several cases of low angular momentum parameter here. We defined the induction of fraction of f. F is equal to 0.4.
Okay.
We tried some parameters like 0.4, 0.5,
Okay.
0.6. We think that 0.4 is suitable for our simulation for the low angular momentum. And
Okay.
this, yes, exactly. This is the fraction we can have. And another very special way to get the standing shock, we did the parameter space investigation is we don't put the smooth accretion flow in the domain, but
Good.
we did the inclination parameter, which means we put the most accretion flow near the equatorial plane.
Okay.
So we define inclination parameter such that, yes, exactly, there is we introduce a parameter of alpha, and then we modify the value of alpha and let the accretion flow to be inclination to the equatorial plane,
Okay.
such that we can get we may try to get the standing shock.
Good.
This is another important point.
Yes.
So basically, we have low angular momentum, and we set the low angular momentum parameter, and another parameter is the inclination parameter to let us put the accretion flow to the equatorial plane. This is
Yes.
two important points for our simulation.
Good. Good. I'm with you. Uh-huh.
And then other things, we just have very normal thing, like we need to say the equation of state that is very usual in any other simulation or works in general. So we have this gamma equal to 4/3, and this is one point. And another point is we may try to consider the different black hole spin parameters. So,
Yes.
so again, we tried A star, that is 0.8, 0.8, 0.9, and 0.94, just
Okay.
to check if our simulation is affected by the spin parameter or not.
Yes.
The final situation is again, this is very traditional when we have a torus, how to put a magnetic field to the torus. So this is a very traditional way, as some other people already worked. We put the A alpha like this way. So of course, additionally we have 4% random perturbation for the gas pressure to
Okay.
excite MRI, but that is just just traditional way, actually MR can be excited by the numerical simulation. So we are not worried about that. The important thing is just we set up the magnetic structure in the torus. That is the important thing to treat the magnetic field.
Cool. I'm with you. Very good. Okay.
Okay, so the simulation results we can get. The first situation is let's see, we have the figure 1. So we have from the figure 1 we see the left panel and the right panel, and this is the typical values. We can distinguish the sine case and the mad case. So we have different inclination parameters, and in the left panel and in the right panel, we have different effect from the black hole spin parameters. And from this figure, we can see which mode is in the sine mode, which mode is in the mad mode.
Yes.
So this is the results we can have. So in this kind of framework, we can see different inclination parameters. So if we have a stronger inclination, means much more accretion matter near the equatorial plane.
Yes.
We get the thin case, but not mad case.
Okay.
Of course, from the right panel, we have some different spin parameters, and we see that just a little bit difference from the spin parameter, and we can see that we of course, if we have a lower spin parameter, we have lower accretion rate. This is we can imagine already. But if we have a bit lower spin parameter, we have a higher normalized magnetic flux. This means if we get the stronger black hole spin,
gotcha.
we may have a thin case, but not a mad case.
Right. Okay. I'm with you. Yes.
Okay, so this is the discussion about the case of mad and the case of thin. And maybe we can go to figure 2 to check the time averaged probability.
Right, average flow.
Okay, we have averaged flow behavior, and we can see this is a figure 2. It is the density distribution and accretion rate distribution. We zoom in the upper panel. That is density. Yes, we may zoom in. For example, we labeled as A, B, C, D. Okay. So we may zoom in, for example, D. We at first beginning, maybe we just say, okay, this is a very usual way we show us the density distribution. It always look like this if we see a normal numerical simulation paper. But if we focus on for example, panel D, the upper panel, exactly, there is some evidence of accretion standing shock. Yeah, exactly. So that part, if some people with free experience, he can identify that could be evidence of standing shock. Okay. It's very marginal, but we can identify. Although it is just a density distribution, but it looks like there could be evidence of that. So that can provides us to dig out the physics behind. So
Good.
this
Good.
even it is a very simple density averaged distribution, but it looks like something is there.
Yep.
So
Definitely.
this is
Okay.
different for the normal density distribution as a
Uh-huh.
normal paper like that. So this is the figure two. Of course, we can see this from the figure two ABCD difference from the inclination parameter of different alpha. So
Yes.
if we have the alpha equal to 50, that is extremely equatorial accretion parameter. So that we can get that kind of standing shock
Okay.
feature.
Thin. Yes. Yes. Uh-huh.
So this is
Uh-huh.
just one way we try to do the parameter space investigation.
Cool.
So
Good.
this is
I'm with you.
figure two, and of course we can try to other parameters like we did in figure three, for
Figure
example.
three, we're going to be changing A star. Mm-hmm.
Yes, again, we can see different black hole spin parameters,
Mm-hmm.
same situation
Okay.
as inclination parameter alpha equal to 50. Again, you can see for example in the upper panel, this is also again density distribution.
Yes.
It looks like because the
Uh-huh.
inclination parameter is the same, alpha equal to 50. So different black hole spin, we always see that kind of standing shock feature. Even at this moment, I cannot say definitely there is a standing shock, but
Okay.
so some
Okay.
hints
There's a hint
we
there. There's a
get.
hint there. Yes. Yes.
Yeah.
Okay.
And we can see we can see figure four, yes.
Right. Which will be okay. Oh, this is the Lorentz.
Yes, which is, for example, Lorentz factor,
Lorentz
the
one.
situation of Lorentz
Okay.
factor, and we
Okay.
want to see the magnetization. So
Right.
this is a traditional way to put the, again, we can see different situation of
Mm.
inclination parameter, the average the
Okay.
distribution of Lorentz factor and average
The
distribution
X there.
of magnetization.
Mm.
And we can see the lower panel that magnetization is equal to 1. So we indicated by the black line.
Yes. Yes.
So we have so we just separate two parts.
Right.
Okay, so this is the situation if we talk about the Lorentz factor and the magnetization.
Good.
And again, we use figure 5 to just to say, okay, we have different effects from the black hole spin parameter, and maybe
Yeah, this is different A.
this
Hmm. Yes.
could be a little bit clear that if we have different black spin parameter and the Lorentz factor distribution, again, we can see that. And also we see, roughly speaking, the magnetization in the lower panel, how the magnetic field, magnetic energy the distribution by different black hole spin parameters. So
Cool.
it's also traditional way, just the people usually want, if they want to check Lorentz factor, if they want to check the magnetization.
Good.
So,
I'm with you. Hmm. Good.
okay, so we can see figure 6.
Okay. Let's go.
Uh,
Shooting shot.
the
Woo.
Yeah, the situation is
Okay.
we can have some hints about the standing shock, but we cannot say there is definitely a standing shock. We need to check the jump of some identified parameters. For example, if how we can identify there is a shock, definitely if we see a velocity, the velocity is not continuous or we can see there is a flow and we can see the pressure. The pressure is not continuous. Then we can identify there is a jump and we can see there's a velocity jump or pressure jump. Then we can identify, okay, there is really a shock there. That is the exactly judgment to say. We say, okay, we have a really shock there. So we check the different inclination parameters
Yes.
for the radial velocity and the pressure. This is one dimension, and again, we can see different black hole spin parameters to affect the velocity and the pressure. We can see if in the radial direction we see discontinuous jump or
Yes.
not. It definitely it looks like we do find the shock there. One shock is in around less than 10
Yes.
G, and one shock is at about 50 to 40 to 50
Very good.
RG.
Yes.
So it is very
Yes.
interesting.
Two in this case.
We found two shocks at a different place. One is near the central black hole, and one is a little bit far away. But definitely, even we can check different parameters, it looks like the two shocks are always there.
Yes. Yes.
This is
But yes. I'm with you.
this
Yes.
is a very important situation that we get. Definitely, this is as the title writing. This is the first time we see the shock in the GRMHD
Very good.
simulation.
Very
Uh,
good.
Yeah, but another question is, yes, you get the shock, but you don't know this is shock, for example, forward shock, reverse shock,
Yes.
transient shock, or it just fixed at a certain position.
Yes.
It is a standing shock or not. We
Right.
don't know. So but we have the simulation at a different time, evolution time. So we can plot the standing shock feature in figure 7.
Very
So from the figure 7, we just pick out one group parameter. That group parameter is, for example, the inclination parameter alpha equal to 50, and the parameter equal to 0.9. Okay, so in this kind of parameter settings,
Cool.
we have the evolution time with the range from 14,000 to 15,000 time interval with 1,000 interval time, and from the bottom to the bottom to top. And again, we see the velocity profile and pressure profile with as a function of radius. And so now I can clearly answer the question. It seems that the shock doesn't change too much with the time evolution. It always seems at a certain position. So definitely I can say, okay, this is a standing shock, but
Cool.
the standing shock is not always at the exact position. It's just some oscillation around the certain position.
Okay.
So this is give us another hint that definitely this is standing shock, but the standing shock looks like a bit oscillation. So this
Yeah.
may let us understand, okay, it is reasonable to link the observationally QPO signature or not. So
Yes.
this is we definitely we found the standing shock here, and we found that the standing shock is just a little bit oscillation, and this oscillation could be related to the QPO feature, which can be observed by all kinds of telescopes.
Absolutely. Very cool. Very nice. Beautiful. Beautiful.
Okay, so for this is our two-dimensional results, we get the standing shock definitely. This is the first
Okay.
time we use the GRMSD simulation to get the feature, and
Okay.
as feature is clearly shown in figure 7.
Yes.
Uh, Another point is some people usually are not satisfied with two-dimensional simulation because two-dimension is not nature
Yes.
alternative. Usually people say, okay, the natural one is three-dimensional case.
Yeah. Yeah.
And we understand clearly that if we want to produce the feature, for example, here we use two-dimensional simulation. We need a very extremely parameter to get the results what we want. But if we want to go to the three dimensional simulation, and maybe the parameters, the values of the parameters could be changed to be, roughly speaking, normal values.
Fair enough.
So we already know. So we perform 3D simulation as
Yeah.
one example, because now we have 2D simulation. We get roughly speaking parameter survey. So we roughly speaking we know the features, and we can easily go to the 3D situation.
There.
So we have the 3D situation, which is shown in the figure
8.
8. Yes.
Yes. Cool. Okay.
So we see the density profile and we see the temperature profile.
Ooh.
Okay, so now we can see it is more clear that we can have the hints from the standing shock. It is shown
Mm,
the distribution. This is much more clear if we can
yeah.
compare to the two-dimensional situation. So now here is the three-dimensional GRMHD, and
Mhm.
we have the reasonable parameter. For example, the inclination parameter is not as large as alpha equal to 50. Now we may have the smaller alpha, which is also means we need a really equatorial plane accretion,
Yes.
but it's not as strong as
Bring it on.
the simulation case.
Okay. Okay.
That could be sounds reasonable.
Yeah. Hmm.
And we this is figure 8 that we can see, and yeah, this is a figure 8 we can see, and for further situation we can see figure 9.
Right. This is an equatorial plane. Uh-huh.
And we can see the radial density profile. And again, at a different time, we can see, okay, we really have that kind of feature.
Ooh, nice. Good. Okay.
So yeah, okay. So we finally identify both 2D and 3D GRMSD simulations. We do get the standing shock.
Nice. Beautiful.
This is very straightforward to say.
Yes.
And
Yep. Mhm.
actually, there is a discussion and summary. Basically, I think this should be talking at the first beginning, like introduction. But I would like to say at this moment, basically, we have some analytic investigations long ago, and people usually say, okay, there should be some transonic points
Okay.
in the accretion flow.
Yes.
But some people argued that if you get even if you get the transonic points,
Okay.
it doesn't mean you get a shock.
Uh,
So
Right. Okay.
Usually people think, okay, we get the transonic point, maybe we can get the shock, but it is not true. So here we really get the shock here. We
Nice.
see the discontinuous velocity profile, discontinuous pressure profile that identified in 2D and 3D GRM simulation, and not only analytical investigation of transonic points. So this is exactly we get. So we can identify, really, we do find the standing shock feature.
Beautiful.
Okay, this is one thing. And another thing is, okay, this can be applied in some statistical objects, like if we have a central black hole, we have the X-ray burst, and from the X-ray burst, we may get something like observational feature, for
Yeah.
example, QPO feature that is
Right.
usually found in the X-ray binaries. And if we have AGN, definitely AGN in central black hole
Sure.
there, and we may consider to some oscillation feature or even some eruption feature that could be linked to the dynamic feature like the standing shock we identified.
Very
So
cool.
this is we put our application hydrodynamic application to the observational astronomical part.
Yes.
So finally, I just to have the summary. One is the low angular momentum accretion. This is one condition. Another condition is we need to put more accretion mass to the equatorial plane to have the
Got
accretion
it.
flow
Got
such
it.
that we can produce the feature of standing shock.
Cool. Okay.
And finally, I would like to thank all the astronomers focused on this topic. We know this the standing shock exciting or not exciting. This is a long-term question. So
Mhm.
different astronomers, different research groups already provided us different opinions. They take great efforts from different aspects. So our work is based on all the things from many kinds of astronomers, research groups. So we really appreciate all of their great efforts before. That we should also appreciate many people, they already discussed many things
Yeah.
before our work. So this is also, at least I should appreciate. Even some different people have different opinions, different people did a different calculation and they get different results. But
Cool.
anyway, we should appreciate all of them.
Well,
Okay, I
that was
think
that was great. That was great. Very good.
yeah, thank you.
That was well,
I think that is a major result of this paper.
very cool. Jirong, I want to thank you so much for walking us through your very awesome article. Very nice. Very nice. Let's see. You touched on it a little bit a couple of times as we went on through. And so let me ask, where do you think we go from here given the published results? Are there additional 3D runs to do? Is there going to be an effort to try and connect the movement of the standing shock with the observations? So just sort of next steps. Where do you think we go from here?
I think it's just the first beginning. We should go on and go further. Uh, as people know, the EHT get great
Right.
results.
Yep.
Of course, again, the major EHT publication is in AAS journals again, so we appreciate uh,
So do I.
that tell us very detailed things near the black hole horizon. So at least my opinion is, my feeling is we still don't really understand the physical process,
Yeah.
dynamic process, and the radiation very, very near the black hole region. That is, we are still not really not fully understand. For example, here we just discussed the sun case or MAD case. So our results is just in the same case. We cannot find the standing shock feature in the MAD case.
Right.
But people always talk about MAD case because usually MAD case can easily produce jet. So this is the point. However, if we talk about MAD case with the jet, we at least until now, we don't find any feature about the standing shock. This is one point. Oppositely, we get the standing shock feature in the same
Correct.
case.
Yes.
So this is it means that same case cannot be simply ignored. And this is also related to the, for example, jet production and something like outflow. So that is a little bit different from the jet. So some physics we don't really understand. In the accretion part, so this is the first thing we can go on.
Okay.
The second thing is if we talk about observational point of view, well, QPO, we need a special frequency. But here, how we can link the hydrodynamics to the exact frequency, that is one point. So
Sure.
different people get a different QPO, but QPO has different frequencies, high frequency QPO, low frequency QPO. But how you can from the accretion disk to get a special QPO frequency corresponding to the observation, that is another important question we should collect. And so there is still a jump from the hydrodynamics to radiation mechanism. Then we can compare. So we have still many things to go on in focus on the accretion disk related to the standing shock feature. Okay, so this is the 2 points I may expect to go on in the future.
Nice, nice. Well, it's going to be very exciting over the next couple of years as we start going down some of these avenues and trying to connect those 2 points you made, both to the simulations and to the observations. So
Yeah,
very good, very cool, very good. All right, Jirong, thank you so much once again.
yeah, thank you, everyone.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Okay, see you. Bye bye.